Hello everyone, my name is Zeping Yu. Today I'm going to introduce our work in EMNLP 2024. The title is Neuron-Level Knowledge Attribution in Large Language Models. This work focuses on how to identify the important neurons in large language models, given a specified input and output. Large language models have achieved very good success, but LLMs still have many problems such as outdated knowledge, hallucination, and bias. For example, when we ask an LLM the president of US, it may answer Obama. Of course, these problems seem to be solved by supervised fine-tuning or reinforcement learning from human feedback. However, these methods may only mask the problems rather than solve the problems. If we design special prompts, these problems still exist. And these methods require designing new data. And in some tasks, it is hard to design the data. Taking gender bias as an example, if we directly use the word man to replace the word woman, we may make an out of distribution data, and this may bring new problems to LLMs. So it is very essential to understand the mechanism of the inner computation in order to design specified methods to solve the problems. The important information of the final prediction is stored in one or many neurons. If we can find the important neurons, we can understand how LLM works by comparing different cases. We can also use model editing methods to modify the neurons containing false or outdated knowledge, or modify the neurons containing hallucination, bias, or toxicity. Moreover, understanding the inner computation can improve the LLM safety. Imagine there is a person understanding the roles of different neurons. He can edit the neurons and put the edited LLM online. When other people use this model, this person can attack it. Therefore, neuron level importance attribution is very significant. Before introducing our method, let me introduce the background about the residual stream in decoder-only LLMs. The final embedding can be represented as a direct sum of many attention head outputs and FFN layer outputs, because each layer output is the sum of the layer input, attention output, and FFN output. The final embedding is used to predict the distribution of the next token over the unembedding space by a softmax function on the multiplication of the unembedding matrix. Another background is about the FFN layer. An FFN layer has two MLPs. The number case subvalue is the number case column of the second MLP, and the corresponding subkey is the number case row of the first MLP. The coefficient score of the subvalue is computed based on the inner product between the residual output and the subkey. Previous studies have found that the FFN output can also be represented as a direct weighted sum of many FFN subvalues, and they also found that many FFN subvalues are interpretable when projecting in the unembedding space. Specifically, when we say projecting a subvalue in unembedding space, it means computing the distribution by multiplying the unembedding space and this subvalue. Similar to the FFN layer, the attention head also has two MLPs, which are the output matrix WO and the value matrix WV. Each attention head output is a sum of many transformed vectors on different positions. And if we split the positional vectors into different attention head subvalues, where the number case subvalue is the number case column in WO, the attention head output can also be regarded as many attention neurons. As a result, the final output can be regarded as a weighted sum of many attention neurons and many FFN neurons. Existing methods have some challenges to locate the important neurons. First, the common attribution methods such as gradient-based and causal-based methods require backward or forward computations. These methods are hard to be used at neuron level because there are too many neurons in LLMs. Second, there is not a unified evaluation metric to compare the attribution methods. Last, the neuron level information flow is not clear. Previous methods can't identify the important neurons in shallow layers because they usually don't contain the information directly. Our work contained two parts. First, we designed a method to identify the new value neurons, which directly contain the important information related to the final predictions. We designed an importance score based on the log probability increase in unembedding space. Specifically, we compute the increase of the log probability when adding this neuron on the previous layer level vector. We compare our method with 7 static methods. In each method, we find the most important 10 neurons, mask these neurons, and compute the decrease of MRR, probability, and log probability of the final prediction. If the decrease is larger, it means the method is better. Here are the results in GPT-2 and Llama. Our method outperforms other 7 methods on both models. And we analyze the distribution of the identified value neurons. All the value neurons are in deep layers, and our log probability increase method can identify both medium and deep neurons. This is also good for the analysis because several studies find that many predictions have been made in medium layers. Then we propose a method to identify the query neurons, which don't contain the important information directly. The query neurons contribute by activating the value neurons. When we compute the sum of the inner product between each neuron and the most important value neurons, we can go back to equations 5 and 6. The residual output is a direct sum of many neurons, so the contribution of a subvalue's coefficient score can be separated into different query neurons' contributions. Here are the results of the query neurons. When we mask the identified top 1000 FFN query neurons, the metrics drop more than 90%. This can prove that our method is useful for locating the important query neurons. Here is the neuron level information flow. First, the FFN query neurons are activated and added into every position's residual stream. Then the FFN query neurons help activate the attention value neurons. At last, the attention value neurons are transferred into the last position and activate the FFN value neurons. Here is the mechanistic interpretability evidence we found in Llama when projecting the neurons into unembedding space. The input is Team Duncan plays the sports off, and the output is basketball. First, the position 3, which is the second BP token of Duncan, activates the query FFN neuron. These neurons tokens are related to basketball after transformation by an attention head. Then attention value neurons and FFN neurons are activated. These neurons' top tokens are also related to basketball. The code is on GitHub and this can be used to analyze other cases. Thank you for listening.